Hey guys, Math 6500 Logistic Regression. This is the first video on Logistic Regression, and I'll let you in on a little something. I'm putting up this video at home. The entire family's home, although I've told them to try to keep it down. We'll see how that happens. Another thing, you'll notice right up here, there's this annoying black mark, and I don't know what that is. I've tried to clean it up, but anyway, no luck. So it's annoying. My document camera in the office doesn't have that, but I'm under a time crunch with some stuff, so I'm kind of forced to do as I have to do. So guys, anyway, we're going to get into logistic regression, and as you've probably seen before, there's a variety of regression applications where the response variable, our y variable, is represented by a binary indicator variable. So instead of our y being continuous, we often have times where our y falls into being either what I would call 0 or 1. 0 typically represents the whatever event we're measuring didn't occur, and a 1 represents that it did occur. Now, if we use just regular simple linear regression techniques, the model that we typically have, where we have our predictor x and our y again is going to be zeros and ones, it's not unusual to run into a model, and let's let that be 1 to be consistent. It's not unusual to run into a model that looks something like this. Well, you can see that if we try to fit this with the standard model, the standard simple linear regression model that we've studied maybe arguably ad nauseum in this class so far, we know that our y sub i's can be found by taking beta 0. Guys, it's really hard for me to see because I'm out of my comfort zone. I'm just going to tell you right now, I'm much more comfortable putting these videos up in my office, but we do what we have to do. Okay. So anyway, the simple linear regression model is like this, and of course when we bring in that y has to be either 0 or 1, we run into special circumstances. Now, we can, well, no, I'll tell you what, I'm going to hold that thought for a little later. Now, what we do in the simple linear regression model is we understand that the expected value of our errors must be 0. So this beast right here essentially becomes that the expected value of our y sub i's can be found by taking beta 0 plus beta 1 xi. All right. Stuff that you know that we again have seen ad nauseum the first 6 lessons in this class. Now let's take this a little bit further. And by the way, I want to let you in on something. I'm going to try to keep my videos around 20 minutes, so I'm going to try to present less material. It seems like when I try that, I end up going an hour, but we'll see. We'll see how that goes. Okay. Now let's consider our y sub i's to be a Bernoulli random variable. And essentially what I'm doing here, if you're trying keeping score and trying to stay, I'm essentially trying to show you why. Tanya, would you let Bailey know about? Okay. That the simple linear regression techniques that we typically use don't work in this situation. So anyway, if we have a y sub I, either 0 or 1, we can define the probability of each of these. So we can say that the probability that y sub I equals 0 is 1 minus pi sub I. And the probability that y sub I equals 1 is just pi sub I. So we only have 2 possible outcomes. So from this we obtain that the expected values of the y sub I And remember again how you find the expected values. You take the value times the probability. So we would have 0 times 1 minus pi sub I plus 1 times pi sub I, which turns out to be pi sub I, which, if you think about this, is nothing more than the probability that y sub I is equal to 1. So it follows that the expected value of y sub I is equal to beta 0 plus beta 1 x sub I, which is nothing more than pi sub I. So it's going to be something. It's going to be something that's going to creep in quite a bit. That's actually problematic for us. Now, from all this, we have things that are problematic. So let's just say we have problems. This could be one of those little sneaky test questions, right? The first thing that we run into is we have non-normal error terms. By now, after completing, for the most part, 5500 and 6500, you know that we want our error terms to be a normal distribution. Well, that's not what happens here. And so what happens is for each error term, so for each e sub I, we get our observed value minus our predicted value. Guys, again, it's really hard for me to see the way the lighting is going on, so please excuse the hesitations here. Can take on only one of two values. Number one, when y sub I is equal to 1, then our error term is 1 minus beta 0 minus beta 1 x sub I. And when y sub I is equal to 0, then our error term is equal to negative beta 0 x sub I. Now, clearly, guys, these e sub i's will not be normally distributed. So the normal error regression model, again, that we studied before, will not be appropriate. Let me grab something that we know that we need from a simple linear regression perspective is we need constant variance. Now, some confusion on constant variance, at least it was back in 5500. Constant variance just says if we plot our errors over, let's just say, our x values, that we expect to see variation the same at each particular x value. So if I come in and choose a random x, I can see that my variation at that particular x is something like this. If I come and choose another x, you can see that my variation varies a little bit, but you would expect that to happen because we deal with samples. But nevertheless, I don't have enough, at least in my opinion, there are formal procedures that we can use to test this. I don't see enough variation to have a concern if this were my residual plot for a concern with concern with constant variation. Now, if I get something that looks like this, where my errors, and I get, maybe a fanning out, and that's kind of the classic case of where we have problems with a non-constant variance, we can see that this particular x, the variance, is completely different than, say, at this. So this would be problematic, right? Whereas this would not be problematic. Well, guys, for the binary response variable, we have that the variance of our y sub i's is clearly going to be the expected value of our y sub i's minus the expected value of our y sub i's squared. I need that to be like that, which in this case will be 1 minus pi squared times pi sub I plus 0 minus pi I squared times 1 minus pi sub I. Or we can look at this another way. We can say that the variance of our y sub i's will be equal to pi I 1 minus pi sub I, which is equal to the expected value of our y sub I times 1 minus the expected value for the y sub I. This should be pretty clear, right? This is the expected value, and this would be the expected value for 1 minus pi sub I. But the variance of our e sub i's would be pi sub I times 1 minus pi sub I, which is the expected value of our y sub i's, times 1 minus the expected value for our y sub i's. Now, kind of a clever way of looking at this is that the variance of our errors is going to be beta 0 plus beta 1 x sub I from before times, okay, so let's make sure this is clear, 1 minus beta 0 plus beta 1 x sub I. All right, so where does this lead us? What we can notice is that the variance in the e sub I depends on our x sub i's. So this tells us that the error variance is going to be different depending on the level, the x value, the x level at which we choose. So guys, that's problematic again. Again, what we're trying to do, we're trying to show why that the simple linear regression techniques that we've learned and spent so much time studying in this class and in previous classes does not work on logistic regression when we have a binary dependent variable. Guys, the final one, the third concern, if you will, is constraints on the response variable. And guys, the response variable, again, in this situation, just represents probabilities. So the mean response is clearly going to be constrained by, which is equal to pi, which has to be less than or equal to 1, because again, it's a probability. And this is a situation that we don't run into with simple linear regression techniques. So guys, I could have gone into a lot of detail here. I chose not to. I wanted to keep it pretty simple. But I hope this, again, the main thing, what have we shown here? We have shown that the simple linear regression techniques that we are so comfortable using do not apply when we have a binary y variable. All right, guys, take care.